Right, at this point we need to investigate how frequency is measured with NMR. Now, frequency is always measured relative to a reference, and there's a good reason for this, in that if we were to put the exact frequencies down on the spectrum, you'll see that you need lots of decimal places to place the numbers on the axis. So your axis will become very full of numbers if you were to use the exact frequencies on the NMR spectrum. So what we do is we use a reference compound called TMS, tetramethylsilane, and that normally has the lowest frequency. It normally has a lower frequency in terms of proton resonance than any other compound you would place in the instrument, and that is a reference frequency. And then the frequency of an arbitrary compound is measured relative to that. So you'll see that the difference between these two is 0.0004 megahertz, and so that difference between 0.0004 and the 400 as a fraction tells us what we're going to call that peak. So you see there's a 400 hertz difference, or 0.0004 megahertz difference, and that actually, if you place that over a megahertz, you'll find that what you end up is 1 over a million. And then if you times that 1 over a million between your difference and your reference, the difference and the reference, and you times it by a million, you'll find that that is a 1 part per million difference. So on the spectrum, we wouldn't indicate it as 400.004 megahertz. We'd put the reference as 0, and we'd put that peak as 1 ppm. So it's always the chemical shift in parts per million is 10 to the 6 times the difference of the signal from reference over the reference, and that will give you a part per million reference. The question is, why else would we use it? And there's an interesting situation we have, is that in a very low field strength magnet, you'll find that you take normal organic compounds, that you'll find the signals range about 600 hertz between the reference frequency and the maximum frequency. In a 9.4 Tesla magnet, the signals range over 4,000 hertz. In a 14.1 Tesla magnet, the signals from an arbitrary organic compound range over 6,000 hertz. So the question is, not everyone in the world has the same field strength magnet or instrument. How on earth could they compare compounds? If you run your compound on one spectrum and it's only in the range of 600 hertz, how can you compare it to run someone who runs the same compound elsewhere on higher field strength instruments? And the interesting thing is that when you convert to parts per million value, you'll find that all signals are in the range between 0 and 10 parts per million of a reference. There's a small reference here, so the 0 to 10 is smaller. A larger reference frequency means that 0 to 10 is further, but you'll find you'll get those compounds in exactly the same range when you work 0 to 10 ppm. So this is an added advantage. It makes it easier to compare spectra coming from different instruments. Just bear in mind that if you've got a compound and you run it on the same compound on 3 different instruments, you'll find that you get matching spectra. So you see this compound has a signal at 0, 5 and 10 ppm. You run it on a different instrument, it's also at 0, 5 and 10 ppm, 0, 5 and 10. But you might realize that the higher field strength spreads out the signals better, so you might have overlap if you run at too low field strength. So there are advantages, there are very good advantages for running at a high field strength, bearing in mind that your E is equal to h nu. Your Lambda frequency is greater at high field strength, and so you will have greater sensitivity as well at higher field strengths. So there are many advantages for running at a high field strength, but ultimately everything is measured in parts per million. Right, now so when you look at any NMR spectra. For example, this is the NMR spectrum, the 1H or proton NMR spectrum for water. And so both of the protons in water, both of 1H nuclei in water give a signal at the same point, and it's measured as 4.684 parts per million from the reference. When you see that 4.684 parts per million, just remember it is from the reference, so just ask yourself, what is the reference frequency? In this case, the reference frequency is 600 megahertz, and so what we can do as well, we can say 4.684 millionths of that is 0.0028106 megahertz, and therefore, if that distance is that, your frequency is the sum of your reference plus the difference gives the exact frequency of the order. So just bear in mind, 0 to 10 is very convenient, but we can always get back to the exact frequency in megahertz should we wish to do so.